Hello, it's Jeff from the Code Saturne development team, and today we are going to go through the famous square cavity tutorial. It will be composed of three main steps. First, the meshing, which will be done with Salome. Then the computation, which will be done with Code Saturne. And then the post-processing, which will be done with ParaView. Please see the links in the description to download Salome and ParaView binaries. To install Code Saturne, you can have a look at those previous tutorials. So let's begin. So I just launched Salome, and now I will go in the Shaper module to draw my geometry. The first step will be to draw a sketch in the OXY plane. So to select the OXY plane, we'll go under the construction menu here and click on the XOY plane. So as you can see here, it's the right plane. So I select it and I click on sketch. Then I click on set plane view to make the view flat. And next step will be to draw my rectangle. To do this, I click on the rectangle item and draw my rectangle and apply. So as you can see, my rectangle appears red now because I have 4 degrees of freedom remaining, as Salome tells me here. So I will have to add some distance and dimensions to this rectangle to fix it. So first, let's for example click on the length item here and select one side of the rectangle. We'll set this distance to 100. Then let's make the same with another side, this one for example, and set this length to 100 as well. And click on apply. As you can see, my rectangle still appears red. Actually it's a square, but it's still red because I have 2 degrees of freedom remaining. I will have to add some distance information. So I'm clicking here on the distance item and I will set the distance of this corner to the YZ axis and set it, for example, to 50. I will do the same for the distance from this corner to the XY axis, and I'm going to set this distance to 50 as well. Now my square is fully located in the OXY plane, and if I click on apply, as you can see, Salome tells me that the sketch is fully fixed and that I have 0 degrees of freedom remaining, so I can click on apply. Next step will be to select our sketch and to make it a part. So to do this, I select the sketch, click on part, new part, and here I have a part made of my sketch. Next, what we want to do is to extrude this part to make a volume. So I'm going to select here the extrusion item and I'm going to select the face of my sketch. Let's say 10 is enough for an extrusion, so I just click on apply. And now I have my volume here, which is well defined, my square cavity volume. So before going to the meshing step, we'll add some groups on this geometry so that later we will be able to define boundary conditions in our meshing process. So I'm just clicking here on the group item. I will name this first group sliding wall. And here I'm just going to select the top face here and apply. I will do the same for the other faces. Group, fixed wall. And I'm going to select this face, this face, and this face. To select more than one faces, I maintain the Shift key and apply. And last, I will add my symmetry faces. Click on Group, name it Symmetry, and I'm going to select this face as well as this face and apply. So now we have our volume and geometric groups on this volume. For meshing purpose, we now have to extract one edges here in the depths so that we will be able to prescribe the number of cells in this direction during the meshing step. So we'll do the same here. We'll select Group. We'll name this Edge, for example. We'll select here the edge type and we'll just select this edge and apply. And now we're ready to go to the meshing step. So from Shaper, I'm going here in the Mesh module. I'm now going to create a mesh by clicking on the Create Mesh item. And I'm going to name my mesh Square Cavity. In the item Geometry, I'm going to select the geometry extrusion 1,1 I created earlier. Mesh type, I'm going to select hexahedral. For the 3D algorithm, we're going to select hexahedron IGK because we want a regular mesh in the X, Y, and Z direction. For the 2D algorithm, we set it to quadrangle mapping. And for the 1D algorithm, we set it to wire discretization. We're going to add an hypothesis to this 1D algorithm by clicking on this item, number of segments, and we'll set the number of segments to 50. Okay, apply and close. Now, if I right click on my mesh and click on Compute, what you see is that we indeed have 50 cells in the Y direction and 50 cells in the X direction, but we also have 50 cells in the Z direction. And we don't want this. We only want one cell in the Z direction because it's basically a 2D case. So to fix this, we'll select our Square Cavity Mesh and click on the Create Submesh item here. And for the geometry, we will select the edge we created in Shaper earlier. Here, for the 1D algorithm, we'll click on wire discretization and we'll add a number of segments, hypothesis. And we'll set the number of segments to 1. Okay. And we will add an additional hypothesis here, which will be propagation of 1D hypothesis on opposite edges, because we only set this hypothesis to one edge and we want all the 4 opposite edges to have the same hypothesis. And apply and close. And now, if I select my mesh, right click and click on Compute, you can see that I have one cell in the Z direction. So here is my mesh. And what you can see also is that Salome here under the group of faces item automatically added the groups we created in Shaper in the mesh module. So if I hide my mesh and I show you the group of face sliding wall here, you can see that it's those boundary faces. The fixed wall are those boundary faces, and the symmetry group will be those 2 opposite faces. So now I can just export my mesh, for example, at the med format here and save. Let's now move to the Code Saturne computation. As you can see, my mesh was saved here, and now I'm going to open the terminal from here, and I'm going to create my Code Saturne study simply by typing Code Saturne create -s, the name of the study, which will be square cavity for me, and -c, the name of my case. Here I will simply type Reynolds 1000 because we want to simulate 1000 Reynolds case, and create. So my Code Saturne study was generated, as you can see, and if I go inside the study, I have the typical Code Saturne folders, the mesh folder, the post folder, and the case folder. So now what I'm going to do is to copy the mesh we created in the mesh folder. So if I go here, I simply take this mesh and I go inside the mesh directory and I copy and paste the mesh here. Okay, so back in my study, here I have now in my mesh the mesh I created. I will now go inside the case directory and I'm going in the data directory, and from here I will open the GUI by simply typing Code Saturne GUI. Let's set up our case now. So under the mesh menu, we are going to select our mesh, which is squarequavity.med. Now we move to the calculation feature. Here be sure that standard Eulerian single phase incompressible is selected. Then under the turbulence model, here we're going to select no model because we're going to simulate a laminar flow with no turbulence. We don't have any temperature field, so here thermal scalar is set to no thermal scalar. We don't have any body forces and we don't have any species transport either. Now, if we move to the fluid properties, we will let the reference total pressure as it is and we'll set the density to 1.0. In order to have a Reynolds number of 1000, we have to put the viscosity to 0.1. If we now move to the volume zones, you can see that by default, you have one initialization zone. We'll click on this zone. And here we'll be able to prescribe the initialization for the velocity. And we'll put 0.1 for the x velocity, and we'll let the y and z velocity to 0. Let's move now to our boundary condition. Here we'll have three different boundary conditions. The first one will be our sliding wall. The nature of these boundary zones is a wall. And the selection criteria here is either a geometrical relation or the name of the zone that you gave in Salome. And here we named it sliding wall. The second one will be the fixed wall. It's a wall also, and the selection criteria is fixed wall. And the last one will be the symmetry. And here its nature is a symmetry, and the selection criteria we gave in Salome was symmetry. Now let's have a look into the details of those boundary conditions. First, here for the sliding wall, we're going to click on sliding wall and we're going to prescribe u, which is the x velocity, to 1.0. So now we have our Reynolds number, which is equal to 1000. And v and w will be let to 0. For the fixed wall, we don't have anything to do. And for the symmetry boundary condition, we don't have anything to do either. So now let's go into the time settings menu. And here you can see that by default, you have a constant time step. We'll change this and choose the steady algorithm. And we'll set the number of time steps to 1000. Let's move now to the numerical parameters. We will let the gradient type here as they are. And moving to the equation parameters, you have the solver menu here, which allows you to change the solver for each variable. We will let it in automatic. And here under the scheme menu, you can change the scheme used for each variable. And we'll use a centered scheme for the velocity, and we will deactivate the slope test. Let's move now to the post-processing menu. Here we'll add some monitoring points. The monitoring points will allow us to check the convergence of the computation. So the first one will be located at 25, 25, 5. The second one will be located at -25, -25, 5. The third one will be at 25, -25, and 5. And finally, the last one will be at -25, 25, and 5. Let's move now to the profiles definition. Here in this menu, you can define 1D profile in your domain. We will define two different profiles. The first one will be the horizontal line that cut our domain in two, and the second one will be the vertical line that cut our domain in two also. So let's define this profile here. We'll choose the CSV format for an output. We'll set the output at the end of the computation. The number of points here will be 50 because we have 50 cells in the X and Y direction. And for the variables output, we'll output the velocity in all the three directions. Now, let's define the line. To define the line, I click on this button here. And here I have to define a parametric definition of my line. So here, X will be 0, Y will be -25 plus or -50, sorry, plus 100 times S. So X will be 0 every time and Y will go from -50 to 50. And Z will set it to 5. Okay. We'll do the same for the second profile. Output at the end of the computation, 50 points. We'll add the X, Y, and Z velocity. And for the line definition, we will this time set Y to 0, Z always to 5, and X will go from -50 to 50, so we'll add 100 times S. S is the parameters, of course, which go from 0 to 1. Okay. So for the other menu that appears in the post-processing menu, you can add a user-defined field. You can add time averages. Here we want a steady solution, so we don't need any time averages. And you can control which variables you want to output in your results. And the same for the surface solution. You can output different variables. So let's now save our setup and run our computation. So we click here on Run Computation and Run Calculation. And here it goes. The computation just ended, so let's now have a look at the results using ParaView. Let's first see if our computation converged well. So to do this, let's open our results folder, and in the monitoring folder, we open the probes velocity x.csv file. Here is a spreadsheet view. We can close it, and let's create a line chart view to have a 2D plot. Here we click on the eye, and here we don't want to use the index for x-axis, so we deactivate this and we use t for the x-axis. In the series parameter, we don't want to plot t over t, so we deactivate t here. And here we have the evolution of the velocity x with the time, and you can see that after 1000 iteration, we are really well converged. We can do the same for the y velocity, for example. So let's open the y velocity here. We click on the eye. We don't want to use the index for x-axis, but we want to use the time. And again, we deactivate time over time here. And again, you can see that we have a really nice convergence of the y velocity after 1000 iteration. So now that we are pretty sure that our computation converged well, we can open the results. So let's create a new layout here with a render view. Click on Open, and here in the post-processing folder, let's open the result fluid domain.case file and click on Apply. Here, yes, here it is. Here is our result fluid domain, and by default you have a visualization of the pressure distribution. We can change the color table here, for example, for this one. And we can have a look at the velocity, for example, and again we're going to change the color table here. And here is our velocity field. If you want to visualize the x velocity, you just click here on the x velocity. Same for the y velocity, but by default it's the velocity magnitude. Now what we can do is that we can trace the velocity arrays, and to do this simply click on the glyph item here, and we're going to deactivate the scale array and click on Apply. Now let's deactivate the result fluid domain.case, and here is our vector field velocity. We're going to scale it down a bit by putting 5 here and apply. And here you have your velocity field. Another nice plot is the stream tracer. So click on the result fluid domain.case and then click on the item stream tracer. And here we're going to draw the streamlines. So by default, it's the seed type is high resolution line source. So we will let it as it is, and we'll set the resolution to 100. That's enough. And click on Apply. So by default, the streamlines are blank. So of course, let's color them by the velocity, for example, and let's deactivate the velocity arrays. And here are the streamlines. Of course, we are missing the secondary motion that appears here because our line source is this diagonal, and you can add another line source in the other diagonal so that you have all the secondary motion that appears. So this is a quite qualitative view of the results. Now, if you want to have a more quantitative view of the results, we can have a look at the profiles that we set up in the Code Saturne GUI. So to do this, let's open a line chart view, and let's open now in the profiles folder the first profile here, profile 1, and apply. The spreadsheet, again, you can close it, and let's make the profile appear. Here, again, we don't want to use index for x-axis, so just deactivate this, and here we want to use y as x-axis. We're going from -50 to 50, and we just want to plot the x velocity. So here is the evolution of the x velocity according to y. So now let's make this plot dimensionless, because here y is going from -50 to 50, and we want y to go from 0 to 1. So here we click on the profile, then we click on the item calculator here, and here we'll simply name this y dimensionless, and here to make it dimensionless we'll type 50 plus y divided by 100. So y is going from -50 to 50, and y dimensionless will go from 0 to 1. And click on apply. Again, the spreadsheet view opened. And now deactivate the profile 1 and activate the calculator we just made. And now what we want to use here for the x array will be y dimensionless, and we will plot this for the x velocity. And you can see here that this time y is going from 0 to 1. And I have experimental results for this square gravity at Reynolds 1000, and I will add them on this plot. I'm going to open the experiment file here and activate it. So for now it's not good. For the x parameter I'm going to use y, and I'm going to plot the x velocity. And here I'm going to not to show the line, and I'm going to add a marker which is a square here, and here are the results. You can see that the line is a computation and the square are the experiment, and as you can see the computation is in quite good agreement with the experiment. So this is a more qualitative comparison of the results. I hope this tutorial was helpful for you. If you have trouble setting it up, you can have a look at the Code Saturne website under the tutorial menu. The link will be in the description. Also, you can have a look at the Code Saturne forum if you encounter any problems. You can also have a look at the other available tutorial if you want more advanced setup. Thank you for choosing Code Saturne, and goodbye!